here. And anyone remember what we described the synapse as? Yep, so we said it's a functional connection between a neuron and another cell that it's signaling, right? Exactly. So we can speak about two types of synapses. We said that we had electrical synapses. And we'll talk about some features there, and then we also have chemical synapses. So we said electrical synapses communicated bidirectionally, so they communicated in both directions. Right? We also said that they used gap junctions to facilitate those electrical impulses moving from cell to cell. All right, so we have the presence of gap junctions here. We also said that the transmission was much more rapid. So there was rapid or faster transmission of signals. Okay, we didn't say much else about electrical synapses, right? We said that they were rare and poorly understood. And we can compare those to chemical synapses that we spoke much more in detail about. We said chemical synapses were unidirectional. So that signal was only transmitted in one direction, and that's from soma down to axon terminal. We said this was a slower mechanism of transmission. Okay, and because it was slower, we also talked about a delay in this transmission. Anyone remember the name of that delay? So it was due to exocytosis. Yeah, perfect. And what was the name of that delay? The synaptic delay, right? We have the synaptic delay, which was due to the time it takes for exocytosis of that neurotransmitter. Okay. We also said the neurotransmitters were involved. These were those signaling chemicals that are stored in the axon terminal and released upon the actual potential arriving at the axon terminal. We also have receptors that are involved here. Right? Over here, we had no receptors, we had no neurotransmitters. That signal just went from cell to cell bidirectionally. Here we've got neurotransmitters. Here we've got receptors. We spoke about two types of receptors last time. Anyone remember the two general types of receptors here? So we said one was fast and one was slow. Yeah, we said ionotropic and metabotropic. And we said that this one was slow, and this one was fast. Okay. And just to kind of describe these here, why they were slow or fast, we said the ionotropic was because the receptor is the channel, whereas metabotropic had to involve other players, one of those important players being a G protein. Okay. All right, so those are the main summary points that we talked about last time in terms of different types of synapses, different types of players involved, neurotransmitters, receptors, and so on. Okay. All right. Let's recall or review one more thing that we spoke about. So we talked about postsynaptic potentials. Right, we spoke about different types of postsynaptic potentials. And we describe these as graded potentials. And we said that they could either be EPSPs or IPSPs. Okay, so either excitatory or inhibitory. So let's kind of describe these here a little bit. So we said EPSPs were a depolarization of the membrane potential, and that there were two ions that are usually involved in an EPSP. What were those two ions? So what two ions are likely involved in an EPSP? So we said sodium or calcium, right? Because of their ECDF, because of their charge, when we open up channels for these two ions, we depolarize the membrane, and that constitutes an excitatory postsynaptic potential. On the other hand, we had IPSPs being a hyperpolarization of the membrane potential. And the ions involved here were usually potassium or chloride. And again, according to those ECDFs and according to the charge, when we open up potassium or chloride channels, we can hyperpolarize the membrane potential, or we can stabilize. We talked about chloride being an ion that contributed to stabilizing the membrane potential. Yeah, so this is what we kind of described. So let's look at some other factors we talked about here. So this is the area that we were really focused on last time. This area where we have synaptic transmission of signals. Okay, this is where we have that chemical signal, that electrical signal, which is the action potential, right? So think about your action potential moving down this neuron, jumping from node to node. That electrical signal was then converted to a chemical signal, and that was transmitted to the second neuron. Okay, so we describe this one as being presynaptic. And we had a postsynaptic. And so the signal is going from the first neuron to the second neuron, electrical to chemical, back to electrical on that second neuron. We talked about what happens on the second neuron specifically. So we talked about IPSPs and EPSPs having the ability to sum. So let's say this was an EPSP, an IPSP, an EPSP again. These had the ability to sum on the second neuron, and then we would make a determination about whether or not this second neuron would also fire an action potential. So what was the area that we said all of these decisions were made? What was the area that we determined whether or not we fire an action potential? What part of this second neuron? Yeah, the axon hillock, right? So this region was the really important region where we had all of those signals coming together. And if at this point we have a threshold stimulus, so above -55, then the second neuron also fires an action potential. And we talked about all the factors that were involved in neural integration. So that included summation, that included facilitation. And so all of that was eventually culminated at this region, and then the determination was made about an action potential. Okay, the axon here.